Welcome to Ask and Learn.
In these exercises, we are introducing a technique for constructing a deterministic finite-state machine equivalent to a given deterministic finite-state machine with the least number of states possible. So we're supposing that M, which is the quintuplet SIF S0F, is a finite-state automaton, and that K is a non-negative integer, and we're letting Rk be the relation on the set S of states of M such that S is related to T if and only if, for every input string x with the length of x being less than or equal to k, f of Sx and f of Tx are both final states or both not final states. And we'll also define R star to be the relation on the set of states M such that S is related to T if and only if, for every input string x, regardless of the length, f of S of x and f of Tx are both final states or both not final states. Okay. Now in part A, we're asked to show that for every non-negative integer k, Rk is an equivalence relation on S. And we say that two states, S and T, are k equivalent if S is related to T. So first of all, let's prove the reflexive property. So let S be a state of M. And let X be an arbitrary string of length at most K. Well, we have that f of Sx and f of Sx, by definition, are both final states or both not final states. Therefore, it follows that Srks is true. So it follows that Rk is reflexive. That was pretty simple. Now let's prove symmetry. So we're going to let A be related to B and let X be an arbitrary string of length at most K. Now, since A is related to B, we have that f of A x and f of B x are both final or non-final. Therefore, it follows that f of Bx and f of Ax are both final or non-final. You can just simply switch the position of the two. And so it follows that BRKA is true, and therefore that RK is symmetric. And one more property we need to prove is transitivity. So suppose that A is related to B and B is related to C, this implies that, well, and we're going to let x be string such that the length of x is less than or equal to k, then we know that since A is related to B, f of ax and f of bx are both final or non-final. Since B is related to C, we have that f of bx and f of cx are both final or non-final. So it follows that f of ax, if f of ax is final, then f of bx is going to be final, and therefore f of cx is final, so that f of ax and f of cx are both final. Or if f of ax is non-final, then f of bx is non-final. And if f of bx is non-final, it follows that f of cx is non-final. So it follows that f of cx is also non-final. So f of ax and f of cx are both final or they're both non-final. So it follows that A related to C is true, and so it follows that RK is transitive. And therefore it follows that RK is an equivalence relation. In part B, we're asked to show that R star is an equivalence relation on S, and we say that two states S and T are star equivalent if S is related to T. So first, let's prove symmetry. So let S be star equivalent to itself. Well, no. Let S be a state of the machine M, and let X be an arbitrary string. And we have the length of X is equal to K. Now, it follows that from part A, we have that S is related to S through RK. So it follows that f of Sx and f of Sx are both final or non-final. This is actually not the way we want to go. What we want to do We know that S is related to S through Rk for all k by the previous part. So we have that since Rk is equal to R star is equal to the infinite intersection of Rk, we have that S is related to S through R star. And therefore it follows that R star is reflexive. Now let's prove that R star is symmetric. So let A be star related to B. We want to show that B is star related to A. So this implies, as we saw earlier, that A is K related to B for all K. But we saw earlier that Rk is symmetric, so then it follows that B is K related to A for all K, and therefore it follows that B is star related to A. So it follows that R star is symmetric. Finally, let's prove that R star is transitive. So let A and B be star related, and B and C be star related. This implies that A is K related to B, and B is K related to C for all K. But then by the transitivity of Rk, this implies that A is K related to C for all K, and therefore that A is star related to C. And so it follows that R star is transitive. And since R star is reflexive, symmetric, and transitive, we have that R star is an equivalence relation. In part C, we're asked to prove that if S and T are K related, then S and T are K minus 1 related. So let S and T be K related for some K. And let X be an arbitrary string of length at most K minus 1. Now, since X is a string of length at most K minus 1, it follows that X is also a string of length less than or equal to K. So it follows that f of Sx and f of Tx are both final or non-final. And again, since we said that x was less than or equal to K minus 1, it follows that S is K minus 1 related to T. Which is what we wanted to prove. Now in part B, we're asked to prove that the equivalence classes of Rk are a refinement of the equivalence classes of Rk minus 1. So we have that strings of length at most k are also strings of length at most k minus 1 are also strings of length at most k. This implies that every equivalence class of Rk is a subset of some equivalence class in Rk minus 1. Recall that the refinement of a partition of a set satisfies this. So we know that strings of length at most k minus 1 also satisfy that the length is also less than or equal to k. Therefore, it follows that Rk minus 1 is going to be a subset of Rk, This implies that every equivalence class of Rk is a subset of some equivalence class. And so the equivalence classes of Rk are a refinement of the equivalence classes of Rk minus 1. I'm sorry, I got this backwards. It should be that Rk is a subset of Rk minus 1. Now, in part E, we're asked to prove that if S is k related to T for every non-negative integer k, then S is star related to T. So let S be k related to T for all k. And let X be an arbitrary string of length k. And in fact, let X be a string of just arbitrary length. Then we have that x is going to be a string such that the length of x equals k for some k. So it follows that since, I guess I'll say k0 for some k0. Since s is k0 related to t, it follows that f of sx and f of tx are both final or non-final. And therefore, we have that, by definition, s is star related to t, since x was of arbitrary length. In part F, we're asked to prove that all states in an R-star equivalence class are all final states or all not final states. So let E be an equivalence class of R star. And let A and B be two distinct elements in E. And since they're in the same equivalence class of R star, it follows that A is star related to B. This implies that f of ax and f of bx are both final states or not. And this is for all strings x. And this implies that every pair of states in E are both final states or both not final states. So all states in E are final states or all are not final states. In part G, we're asked to prove that if S is star related to T, then f of S A is star related to f of T A for all input strings or for all letters A. So let S be star related to T and let A be a letter. Now, we have that f of s x and f of tx are both final or both not final for all inputs x. So it follows that f of s ax and f of t ax are both final or non-final for all strings x that are inputs, but this implies that since f of s ax is equal to f of s a x, by a previous exercise, it follows that f of s a x and f of t a x are both final states, or both non-final for all inputs x, and therefore we have that f of s a is star related to f of t a.